All right, thank you all very much for your interest in our webinar where we're going to be discussing the CAD-based design optimization of a race car front wing. This work was done for the 2020 SAE World Congress in Detroit, and a technical paper of the same name was written and accepted for publication for that conference as well based on this work. One additional note before we get started, I did want to mention that if you have any questions, you can type them into the comments section if you scroll to the bottom of the page. Additionally, you can email us, and I'll be sure to provide email addresses at the conclusion of the webinar. So with that, I'd like to take a moment and introduce all of the participants and co-authors for this work, starting with Ilya Tolchinsky. Ilya is a lead application engineer for Phoenix Integration, the developers of Model Center. Ilya began his career as an aerodynamicist working for Rolls-Royce Engines, and throughout his career has helped develop various engineering design tools primarily in the aerospace sector. For the last 6 years, Ilya has been working with Phoenix Integration, helping engineering firms understand the potential of process integration and design optimization while applying this technology within their businesses. Thanks for joining us, Ilya.
Thanks for having me.
My name is Travis Kerrigan, and I manage the business development team at Pointwise, and this involves working with our prospective and current clients to strengthen and improve their CFD process, as well as working with our software partners to demonstrate best meshing practices. And I'm joined by my colleague Josh Dawson, a senior applications engineer on the business development team at Pointwise. Prior to working with Pointwise, Josh worked as a Department of Defense contractor where he simulated extreme thermal environments following explosive detonations. Thanks for joining us, Josh.
Thank you, Travis. Thank you, Ilya.
All right, so with that, I'm going to go ahead and pass things over to Ilya, and he's going to start by talking a little bit about the application. So, Ilya?
Thanks, Travis. As Travis mentioned, my background is in aerodynamics, primarily in the aerospace industry. And I wanted to use my background, my experience, and apply it to an automotive problem. And while doing this research, I came across the aerodynamics for race cars, particularly Formula One race cars. Here, aerodynamics play a critical role for the performance of the car and the team. And a lot of money and research and time and effort is put into the design, the aerodynamic design of the car. In particular, the front wing is responsible for a third of the downforce of the car, and a lot of effort is put there. If we look at the lineup, we see a lot of very complex, very advanced aerodynamic shapes, but there is no consensus to a good design. In many other areas, including other parts of the car, there seems to be an established and accepted best design. But here, it looks like we haven't converged yet. And so this looks like a great problem to apply optimization techniques to. Now, if we look at the fundamental properties of a wing, the first order effects are primarily due to the load distribution across the wing. So which part of the wing is doing the most work. And we can easily, or we can simulate this by taking a constant section and just varying the twist. This allows us to dial in where the wing generates lift or downforce. And so by taking this approach, by simplifying the problem and looking at just the twist of the wing, we can answer a fundamental question. Is it better to have a larger loading at the tip or root of the wing? Or is it better to have a larger angle of attack at the root or tip? And so here we're going to address this problem, and we're going to use Model Center to build an automated workflow and then find the answer to our question. If we were doing this in the old days before we had simulations and analysis tools, we would build a physical rig and try different shapes in it. Today we can do this by building a virtual rig and analyzing it using simulation tools like fluid dynamics analysis. So I start out here with building a virtual rig using CATIA, and we can see here a simplified Formula One car with a two-section front wing. I modeled just the elements needed to model the effect of the twist on the wing, and effectively the root and tip angles become my variables that I can control. Here we can see the extent of the design space, how much I can vary this geometry, the maximum and minimum angles of attack that I can create with my macro. We can see here that how this wing is generated. I use Excel to specify the cross sections. I can dial in the angle, and then I have a macro in CATIA that brings those sections into CATIA and builds a 3D shape. And here I actually managed to create a generic method for creating a 3D shape that can be constructed through parallel sections, which is just about any 3D shape. The next step is to take that geometry and mesh it. And here I partnered up with the guys from Pointwise who helped me create I would say a modern mesh for this type of application. And I'm very, very grateful for their help and involvement here. I think the partnership worked really well. And normally this is a big challenge for doing this kind of automation. The meshing is typically a stumbling block. It's difficult to automate, and I think this went really well. But I'll pass it over to Travis to describe the details of what we did together.
Thank you very much, Ilya. I appreciate it. So to start with on the meshing side, we began with importing the geometry from CATIA and started with the surface mesh. And Pointwise was used to generate both the surface and the volume mesh, but the surface mesh kind of serves as the basis for everything that we did from there on, the volume meshing, the parametric mapping, which we'll talk about in just a minute. So for the surface mesh, our goal was to create something that accurately resolved the geometry, but also remained coarse enough so that we could rapidly study all the varying designs and get a good idea of what the delta was between each design. So we chose a boundary conforming advancing front surface meshing algorithm consisting of all triangular elements that you see in that image. And then more specifically, near the leading and trailing edges, we anisotropically stretched these triangular elements into right-angled triangular elements to more accurately resolve the high curvature areas, the small features, using much fewer cells than would have been needed if we had resolved that more isotropically. Once the surface mesh was created, the next step was creating the volume mesh. And the key with the volume mesh is to isolate the vehicle or the region of interest that's going to be changing from design to design such that we could minimize the mesh and solution variability during the optimization process. So the deltas that we're seeing between designs are related to the design itself rather than the changes in the actual meshes. So to do this, we have a near field region around the vehicle of interest. That is a hybrid viscous block consisting of prismatic elements in the boundary layer generated automatically using our anisotropic tetrahedral extrusion algorithm that transitioned to kind of an isotet core. And then outside that, we have a static far field consisting of all hexahedral elements, and that region of the mesh will remain static from design to design. The next step was the automated remeshing. So we began by creating that first mesh for the baseline design, the surface mesh and the volume mesh, and isolating the vehicle itself inside of its own core block. For each additional design, there was already a mapping between the surface mesh and the parametric geometry. And the surface mesh and the geometry actually shared identical topologies. So there was this nice UV parameter mapping between the two. So using our scripting language, we could take that baseline mesh and simply map it directly onto any updated design and then just regenerate the volume mesh completely hands-off. And this was really important for the optimization process as we had to pull the engineer out of the loop entirely. So we built the first baseline mesh that had a nice parametric mapping to the geometry. We update the geometry, map the mesh onto the new geometry, and then reinitialize the volume, all completely behind the scenes using our glyph scripting language. So with that, I'm going to pass things back to Ilya to discuss the CFD setup.
Thanks. So now we have a method to automatically update a mesh when the geometry changes. The next step is to run the fluid dynamics analysis. For this, I took a speed of 100 miles an hour where the aerodynamic effects become significant. You can see here I modeled the floor and the spinning wheel to model the wall effects correctly. We used AccuSolve to run the analysis, and each one of these analyses took about 6 to 8 hours of computational time on one of my laptops. So we have I described all the individual bits. We need to put them together in an automated workflow, and we did that using Model Center. Once we're able to do that, we can now run a lot of design points if we have sufficient computational power, and we can do things like trade studies and optimization. Just to show what the workflow looks like, you can see we can have interactive geometry, so we can examine what our CAD looks like. And then we can see here components linked together from Excel to CATIA to Pointwise meshing to AccuSolve, and finally post-processing. You can see we can also pull out the results back into the workflow so that the user can easily see the performance of the current design. Now, as I mentioned, I was doing this on my laptop, so I had 3 available laptops and only 1 CATIA license. I had 3 AccuSolve licenses. So I needed to figure out a way to use all my computing resources effectively. And so I had to come up with a way to queue my CAD evaluations while running the CFD in parallel. And Model Center allowed me to set up such an ad hoc network. So to explain how this works here, so we start with the first geometry. It's run on laptop A. We create the CAD, and that starts the run on the same machine. And now that we have a free CATIA license, I can set up another geometry, pass that to my second laptop, then create another geometry, and start the third run. Now all 3 runs are running in parallel, and I'm using all my available CPU. Now they can finish at any time. So let's say B finishes first. I then have the workflow create another CAD model and then load up the available machine. Still, with 3 laptops, I was heavily resource constrained, so I had to figure out how to solve this with a few evaluations as possible. So the first thing I did is I ran a parametric study on a symmetric or on an untwisted wing, varying just the angle of attack. This allowed me to identify a region of interest around which then I varied the tip and root angle individually to see how that affects the airflow. If we see here, we have the region of interest highlighted from about angle of attack of 15 to 30. I have my downforce increase significantly, and then any further angle of attack disrupts the lift or downforce. And so I chose to run my design of experiments in that region, varying the root and tip from 16 to 32 degrees. And after I ran this design of experiments, this DOE, I then had a table of data. And in this case, I can use our contour plots to visualize and understand the design space. Here I'll show the video of setting that up. It's actually just real time because I wanted to show you how easy it is to set up this kind of analysis. So here we have a contour plot. On the lower part, we have our root angle of attack. On the y-axis, we have our tip angle of attack, A1. And so the upper left region of the screen represents an angle of attack that's higher at the tip than the root. You can see I've set up, I'm plotting both lift and drag together. Drag I set up as a constraint using my baseline design as a reference point. So I wanted to see how I could increase my downforce without increasing my drag count. And we can see here that same plot. And as I mentioned, the upper left part of the screen represents tip angle of attack higher than the root angle of attack. And we can see here that our downforce values are higher in this region. Yep, near the top there. And in fact, the region with the highest downforce appears to have a lower value of drag than our baseline. So it actually can improve on that. So I can improve on the downforce and improve on the drag at the same time. And if we also further think about it, it looks like the best value might actually be at even a higher angle of attack at the tip that's outside the perimeter of the study that we did. Here we can see the streamlines going across the wing for the best design that we found. Here we can see the velocity profile as we go from the center line, the symmetry line, to the outside. And then the same going from the front to back. So with this initial study, we can see that angles of attack that are higher at the tip give us better results. So loading the wing up at the tip where it goes around the wheel gives us better results. And for me, this makes sense intuitively. The airflow is already disrupted around the wheel, which is not aerodynamic. We need to somehow get the air over this wheel. And if we see here this cross-section, that the second wing is kind of a bridge for the airflow to get over the wing. So I think these results are correct, but it's just the beginning. We need to continue with a more realistic, more complex geometry. Now, in reality, we also need to consider the aerodynamics of the whole car, because things you may do up front have an effect downstream, and you may want to actually be using the airflow to control the airstream, the downstream airflow. The powerful thing about this method is that we start with a CATIA geometry, and the final result is the CATIA geometry. Often optimization is done on the mesh, and so at the end you have a modified mesh, but then you have a manual step of bringing that mesh back into CAD that can be manufactured, or it can be used as a starting point for analysis for other disciplines. So this methodology of starting with CAD and going all the way through in an automated process also allows you to bring the aerodynamics together into an analysis with the other disciplines, allowing you to consider all disciplines at the same time, likely getting gains that you cannot get by analyzing the individual disciplines as is traditionally done.
All right, thank you very much, Ilya, and thank you all very much for taking the time to watch our webinar. If you do have any questions, like I said, you can scroll down to the bottom of the page and leave them there, or you can email us. If you have questions about the application itself or the optimization framework or model center, you can contact Ilya at Phoenix Integration. There's his email address. And if you have any questions about Pointwise or glyph scripting or the meshes made for this, you can email myself or Josh at letstalk@pointwise.com. So once again, thank you all very much for taking the time to watch our webinar.